Hello everyone and welcome back to That Engineering Girl. For those of you who don't know me, my name is Ruha and I am an electrical engineering student. I just finished my third year and I'm currently on my internship as an embedded software developer. Now I'm out here sharing my journey, engineering my life, both literally and figuratively. So what are we talking about today? So recently I was thinking about all of the cool things I've learned in my engineering degree so far, and I realized they're actually not all in electrical engineering. I've learned some really cool things in other engineering disciplines that come up from time to time in my actual life that I actually think about, like, oh, I've learned about that and I'm seeing it right now. So today I thought I'd share my favorite engineering concepts from different engineering disciplines, including civil, chemical, mechanical, software, and of course, electrical engineering. So without further ado, let's get into it. Okay, so the first discipline that I want to talk about is civil engineering. Now, in first year of engineering at the university that I'm at, which is the University of Calgary, you have a general year in which you get to explore the different engineering disciplines and take courses from the different disciplines. So I got to take a statics course. Now I'm not sure if statics is the correct word for the actual course content, but that's what the course is called. In there, I learned something that has stuck with me this entire time and I think about all the time. And that is center of gravity. Now, for those of you who haven't heard of this term at all, I won't pretend that I'm an expert in this, but from what I know, essentially what that refers to is that at the point of center of gravity, which is a distinct point in an object or, you know, whatever you have, like for example, there's me, I have a center of gravity, say, I don't know, right here. This is not true, I'm just making a pretend belief. Let's say I have a point on my neck and that's my center of gravity. Now, theoretically speaking, I could get a pivot point, a beam, support, whatever it is, and I could place it right at that point and you could balance that object. So in this case, me, you could balance anything at its center of gravity, which I think is so cool that you could have the most complex structure, but if you can find its center of gravity, then you can balance literally anything by just putting a pivot or support at that one point. I think that is so cool, and why I think about this all the time is because I practice a lot of balance work and strength training, so I'm really working hard to improve my balance, and so this is something that I think about all the time when I'm doing that sort of training. Okay, so let's move on to chemical engineering now. So in my intro to chemical engineering course in first year of engineering, I learned about laminar versus turbulent flow. Now, I'm not going to once again act like an expert in this topic, but from what I know is turbulent flow is much faster flow, so a fluid, liquid that is running or flowing at a specific rate. They have a threshold where at that threshold anything below is laminar flow and anything above is turbulent flow. So that's the difference between the two types of flow. Laminar is slower, turbulent is much faster. So the cool thing that I learned in chemical engineering that's related to laminar versus turbulent flow is stationary laminar flow. Now this is a specific type of laminar flow where you have a fluid that's actually running and flowing, but it looks still, which I think is so cool. And this is actually a pretty popular topic on the internet. You can easily search up, you know, stationary laminar flow video. There's many online which actually show that you have water running, but it looks like it's still. It's frozen water. It's such a cool experiment, such a cool idea, so I absolutely love it. All right, let's move on to mechanical engineering now. So this is something that I use actually a lot when I open doors. And you'll understand what I'm talking about when you hear the idea. So the idea is torque. And torque is essentially a rotational force. You can think about it like that. You apply some sort of force and it causes some sort of rotation. That's torque. It's not a force. Torque is not equivalent to a force, but it's the result of a force, so rotational force. And the actual formula is force times distance, but I digress. My point is, the important thing to note is from your reference point, if you apply the same force, then the farther you go, the more torque you produce. So the more rotation you produce. Now, I think this is so cool because every single time I open doors, I try to open them from the farthest I can. So you know how usually you have the hinges here and then you have the other side of the door? Try to open them from the farthest you can because you will produce more torque, which means you can open the door way more easily. Try this out because the closer I move to the hinges, the more harder it is to actually open the door. And I love the whole idea. I love the idea of torque. Okay, next up is software engineering. So slowly we're moving into my discipline, and especially because currently I'm working as a software developer. So what is my favorite thing about software engineering? Well, in my computer organization course, which I'm cheating a little bit because computer engineering is a mix of electrical and software, but this is software related, technically, and that is assembly language. Now, assembly language, what is it? It's essentially the low-level instruction set that your computer uses to actually process and run your code. So whatever software you're developing, it could be C++, I don't know, Java, whatever it is, you compile your code and linking and everything happens. And essentially at the low level, what that's doing is it's converting your code into assembly language. So it's converting your code into basic instruction sets that your computer uses. There's some very basic instructions that your hardware can process, and so that's all converted. All of your code, all of your complex code is converted into these basic instruction sets, and then your computer can actually understand what you want it to do, and it can then run that code that you're wanting to run. It's so cool, and hopefully I explained it right. But assembly language is something I absolutely love because it really allows you to imagine how the software and hardware are actually interacting. How does your software run on your hardware? How does it become into something that your hardware can understand and actually process? I think it's such a cool thing. And one thing to note is it's very specific to the machine that you have, because it's very processor dependent and architecture dependent. I think that's the more correct way to say it, is it's architecture dependent. So that is my favorite thing that I've learned in software engineering. All right, I saved the best for last, and that is my favorite thing that I've learned in electrical engineering. Of course I had to save it for last. It's finite state machines. Now, finite state machines, the best way for me to explain them is it's a system, a digital logic system, and I'm already making this very complex for people that aren't familiar with digital logic. So let me rephrase that. So it is a system which whatever state it's in is dependent on its previous state. Now, for example, let me give you an example. Say you have a timer that counts up to 5. Let's say your current state is you've counted up to 3, let's say. So then your next state is going to be 4, which is dependent on the fact that your previous state was 3. So it's dependent on what's previously happened in your system. That's essentially what a finite state machine is. It's dependent on what's currently happening and also what previously happened in your system. Now, at a technical level, this is done in digital logic, and what a processor really is a really, really, really large finite state machine. And anything useful, well, actually, let me rephrase that. Most of anything useful that you can do in digital logic is somehow related to a finite state machine. And they're so interesting because they look very, very complex, very easily, and you can easily produce an extremely complex finite state machine. But if you think about it in the terms of, okay, what state am I in? And what state am I going to go to if this happens? Because then there's events, then it becomes so much more logical and clear, and it's so interesting. And especially interesting because I'm obsessed with processors. So I just love the whole idea of finite state machines and how they're so prevalent everywhere. Like I said, anything useful, most of anything useful is somehow related to a finite state machine. And they're so cool. So go search one up actually if you're interested, because I promise you will be baffled by what you find. Alright, so there you have it. Those are my favorite engineering concepts from different engineering disciplines that I've learned during my engineering degree. So with that, I hope you've had some fun. I hope you've learned something new in this video. And until next time,